Welcome to Nexthermal's presentation on how to target heat to reach higher performance. I am Jeff Wheeler, Vice President Operations for Nexthermal Corporation. We are very excited to present this to you, and it's our hope that you find these topics informative. Sustainability initiatives are leading innovations in materials processing. System buyers such as Director of Engineering for a major consumer packaged goods producer are now demanding that the total cost of ownership of the machine includes a definition of energy usage. In many processes that use thermal energy, the cost of creating the energy is the leading operating cost in the production process. Using smart electric heating methods compared to natural gas or hot oil, the application can be targeted for best results and controlled more consistently. This is part 3 of a 4-part series that covers a review of the parts of electrically heated system, the durability, and how to increase efficiency, with a final review of a case study of a high-performance heater. This session will start with a review of what we mean by high performance when we talk about the use of electric heaters and tools. We will then review what things can be done in the design to increase efficiency of a tool using electric heat. What do we mean when we say higher performance? Let's take a minute to define this in terms of heating the systems. Less cost means to focus on the total cost of operation of the heater and the tool, saving energy and limiting heat energy waste. Installing reliable solutions that lower service costs and allow for more uptime. Supporting lower count of service parts in stock. Fast delivery rather than spare parts inventory that consumes capital and ends up getting lost anyway. Faster production means higher processing speeds, which allows for more production per unit of machine time. Lower scrap from defective product means more revenue per production run. And more consistent output can provide lower risks to packaged product for recalls or spoilage. Compared to other methods of creating thermal energy, electric heating is unique in that by definition, it is 100% efficient. With the range of heater sizes available today and the design flexibility that electric allows, it's possible to target where and how much thermal energy is needed for the highest performance of the final system. To recap the series, in part 1, we reviewed the previous parts that form a thermal process and the roles of each. In part 2, we reviewed the topic of durability and the influences that we can make in the choices of materials and use of them. Now to move to the topic of this presentation, to increase efficiency, we can discuss 3 areas. Design of the mask, considering features that might block the timing of the thermal energy to the working surface, the fit of the heater to allow for thermal energy transfer, and the position of the sensor to balance between the surface temperature and the heater power. Severin's on process problems tends to be the focus of more power. While there are cases where more power might be appropriate, ignoring the other parts of the system could net you at best a marginal improvement or at worst an uncontrollable temperature. So let's review the impact of that choice. Increasing the wattage of a heater allows for a higher rate of rise, either in heat up or recovery to set temperature. In most applications, if the duty cycle of the PID controller is between 60 to 80% on time, the wattage in the system is well suited for the mass and heat loss. A good rule of thumb is if you find your timing is on more than 80%, or if it's taking too long to reach initial set point, you need more power, as the loss is outpacing the capacity of the heater to deliver, or perhaps even less mass in the system. More power does not fix uniformity of the working surface. In fact, it can make it worse or make the sensor read better. More power does increase the core temperature of the heater. It increases the amperage on the circuit. It can shorten the PID tuning and clip the power faster to the heater, making it harder for it to control. And it can also warp sealing surfaces via thermal stresses or damage the attached components. Let's start with a review of standard heater without distributed wattage. Without that adjustment, as noted, there is a significant temperature drop-off on the ends due to higher heat loss. Total temperature difference shown here is about 35 degrees C. Why is that so when the heater has uniform wattage profile? Heat moves through a design like water. Features such as holes and corners block thermal energy from moving through the part. Fourier's law of thermal conduction states that the time rate of heat transfer through a material is proportional to the negative gradient in the temperature and the area at right angles to that gradient through which heat flows. Thermal energy is transported through metal by migration of free electrons from the ions and lattice vibrational waves. Unique to metals are delocalized outer shell electrons which can freely move. The higher the free electrons, the higher the heat current through the lattice, which is why you see in pure metals like gold, silver, and aluminum has the highest thermal conductivity. Here's a loop for the first 1.4 seconds of a jaw being heated to show how thermal energy travels throughout the part. During the on time, the power to thermal energy is being distributed through the jaw mass in this way. Based on this, we can review some design choices in more detail and understand how they impact performance. When heat is removed through either convection to the environment or conduction, which is contact through mounting locations or to the film, the thermal energy loss must be replaced by the heater cycling to maintain a set point. But as a wave, it is time-bound, thus comes as a delay within the mass. Features such as holes, pockets, and edges block thermal energy, creating a wave around that feature. Dry air, like around a screw thread profile, is an excellent insulator as well. The fit of the heater to the mass has a direct impact on several things. Internal temperature of the heater, a response to the heat recovery to the jaw. The loose heater is easier to remove on failure. However, a rule of thumb is that at typical watt densities, for every 1,000th inch of air gap can increase the steady state temperature of the core 200 degrees Fahrenheit. For example, consider a customer has a heater running at 600 degrees F or 315 degrees C on the heater case. Assuming that the heater case is at 129 watts per square inch, in a perfect press fit, the core temperature would be 405 degrees C. Adding a 1,000th fit, or H7G6 class, to the example will increase the core temperature an additional 93 degrees C, raising the core temperature to 516 degrees C. With thermal delay, this will overshoot even higher. Raising the watt density from 129 watts per square inch to 160 watts per square inch and allowing a 1,000th inch slip fit brings us to 537 degrees C. To show the codependency of watt density and fit, lowering the watt density to 65 watts per square inch will lower the temperature from the press fit example at 405 degrees C to 360 degrees C. However, adding in 0.2 millimeter clearance, so 8 thousandths of an inch, raises the core temperature up to 760 degrees C. Maximum surface temperature in nichrome wire is 1200 degrees C. All these simulations were based on steady state temperatures. Any tool operates in a dynamic environment, so that gap between 1200 degrees C and 760 degrees C can easily be closed during a thermal overshoot. The position of the sensor needs to balance between the surface temperature and the heater power. Better control will result in a lower scrap. The sensor is the control signal back to the PID controller, which modulates the power to the heater. This modulation limits the on-time of the heater, effectively managing how much thermal energy is created into the jaw. Placement is decided by what it is you're intending to read, working surface of the face or internal to the heater. Working surface temperature is where the film material is being formed, but the lag time from the heater is typically too long to be well controlled. Heater temperature protects the heater from overshoot, which can protect the heater from damage, but the working surface temperature is no longer accurate. The ideal is a balance between the working surface and the heater. Note in the graph shown, there's a relationship with the heater and the sensor. The heater is at 1/3 diameter with a block thickness. That is so that there is enough mass around the heater to absorb the thermal energy and dissipate it accurately. The thermocouple is on the edge of an arc from the working surface into the block, equidistant from heater and surface. In this design, the thermocouple is measuring the same temperature as the working surface and the majority of the mass at the same time. Sensor depth also plays a role in the accuracy of measurement. Taking the same model and slicing it crosswise, we can see the sensor location in relationship to the heat pattern. Decisions must be made if the sensor is tip sensing as well. Mounting of the sensor can also influence if the tip is shaped the same as the pocket, if it's a drill point or radius, and if it's spring-loaded to improve surface contact at the tip. There are also designs that use a copper plug at the tip to improve responsiveness of the sensor as well. Unless it's an RTD type of sensor, electrical considerations must also be made if the sensor needs to be grounded or not. The controller type will dictate if the sensor needs to be electrically grounded or not to properly isolate EMF noise. This model is 100 millimeters or 4 inches edge to edge and would represent a top sealed head that has 4 equal sized portion pockets in the center main ingredient pocket. This would be an example of an application where a food product is being packaged into a tray format, like chips and 4 different types of salsa. Then the film needs to be sealed to the tray. Additional design features in this model is a top cover plate to seal the backside, which would normally draw heat off the sealing plate. Through design features, we can limit the heat transfer and improve thermal efficiency and improve the response rate between the operations. As you can see from the left side image, the thermal simulation shows the critical seal area being uniform temperature and significant temperature drop in the ingredients pockets. This would be important, for example, to protect the salsa or chips from burning during the sealing process. This design will use a simple intercut groove to slow down heat transfer from the heater location, shown in red on the right side, to the rest of the plate mass. In the center pocket, we reduced almost 40 degrees C, with further reduction possible with more groove development. The heater shown in this example is Nexthermal's 1/8 inch diameter coil heater, pressed into a groove to retain it. This heater can be made with an integrated thermocouple inside the heater, making sensing options easier, and it can be fully sealed for washdown protection. These heaters are custom made to any length, watts and volts to 480 volts, and available in a range of diameters in a fully annealed condition that can be hand-formed into complex shapes. Key to efficiency is targeting the thermal energy to the working surface. Note the top surface of the head is operating above hygienic conditions to present a safe production environment without having significant heat loss to non-working surfaces. The cutaway view on the right shows one method we can control in this example by using opposing angles at contact points, which allow a point-to-point contact for heat transfer, as well as a great sealing surface for contaminants without adding additional gas to the. Sometimes there are unique shapes that require a design feature to seal. This example is a tool that could be used to form a gusset in a pouch or a seam weld. This example is also 100 millimeters, 4 inches long, by 4 millimeters thick, with the top angled edge that is the working surface. Here we have indirectly heated areas as well as varying mass for heat transfer. The flange ears on the backside would be for mounting to a machine and accounts for heat loss in the model as well. For very small parts, a mini heater can be a great solution. 2 options are possible. 1.8 millimeter diameter to 70 thousandths of an inch, and 1.4 millimeter diameter, which is 55 thousandths of an inch, which are also pressed into melt slots into the tool. Employing strategic heater positioning and incorporating design slots can help focus the heat where it's needed. Recall that heat energy is transmitted through the part in waves. Operating the tool in a cyclic process where heat is being removed through time-dependent contact, like forming a seal, you can be very clever in timing the pulses of that heat energy to arrive at the working surface in a uniform way. Tools don't work in steady-state conditions, and that's commonly overlooked when applying PID control heat to maintain set point. It is hoped that our conversation about what efficiency means in the world of heaters and how to increase efficiency in tool design choices was valuable to you. Continuing the discussion in part 4, we're going to talk about a case study of a simple material change that can net a performance improvement. On behalf of the team at Nexthermal, we thank you for your time and look forward to seeing you in the next video.